This is part 4 of the Chapter 2 summary for the Deep Learning book, authored by Ian Goodfellow and others as presented on screen here. In this video I'm going to continue from where I left off previously, having reviewed the pseudo-inverse method using the singular value decomposition. This video is easier than the previous couple of videos as I'm just going to discuss a couple of quick concepts presented in sections 2.11 and 2.12 of the Deep Learning book. In the following video I'm going to review an example of principal component analysis as presented in the book, which is not so succinct as this introduction to these concepts, so that will follow. So, the first is the trace operator. On the face of it, this operator is pretty simple, but nonetheless it's not trivial. It serves as a good tool for the manipulation of algebraic statements. The trace operator is a function that returns the sum of the diagonal entries of a matrix from top left to bottom right. It should be noted that it's only defined for square matrices, and the trace of a scalar is just itself. Its strength is in allowing you to refer to other operations that would require cumbersome summation notation otherwise, such as the Frobenius norm. If you'll recall, the Frobenius norm is the square root of the result of summing the square of each term in a matrix. This is a mouthful, but it can be encapsulated with the trace operator as seen on screen here. This kind of usage is interesting because it isn't necessary to compute the entire result of matrix multiplication to have the result for the trace operator. In this case, the multiplication within the trace operator is just a shortcut to retrieve the dot products for each column vector with itself, and those end up lying along the diagonal. In the same way, trace operators can be frequently seen in generalizations from vector operations to matrices. The trace operator has a number of properties which are important to understand. It's these properties that make it a flexible tool in being able to manipulate various algebraic statements. It's a linear mapping, so it has the properties of being additive and linearly scalable. So the trace of a plus b is equal to the trace of a plus the trace of b. And the trace of scalar c times a is equal to the scalar c times the trace of a. Because it only draws on the diagonal data in a matrix, it is invariant with respect to transposing the argument. So the trace of A is equal to the trace of A transpose. It also has the property that if the trace is being taken of a series of a product of multiple matrices, the result is the same no matter how you cyclically permutate the sequence of matrices being multiplied. That means that you can move around the sequence of multiplication, cycle it around, so long as the sequence always repeats the same pattern if you keep repeating it. Alternatively put, as you can see on the screen here, if you took a sequence of matrices being multiplied and repeated that sequence out infinitely, the trace operator would be the same for any subsequence of the same size taken from that repeating pattern. So combining these last two properties allows for a given trace operator on some argument to be expressed in a variety of different ways, and that flexibility can be leveraged to simplify equations or to make equations more aesthetically pleasing or more aligned with intuitions, whatever the case may be. We'll see an example of that in the next video. So, following the section on the trace operator in the text, it refers to a section on the determinant. I already reviewed the determinant in my last video because it was relevant then, but I'll review it here as well. On the surface, the determinant is a function that maps a matrix to a scalar value. Fundamentally, the value of the determinant is a measure for how much the matrix stretches space. If the value is less than 1, space gets compressed. If it stays at 1, the space stays the same in terms of area or volume. And if the determinant is greater than 1, the space gets stretched. If the value is negative, that means the space has been flipped around. Lastly, if the value is 0, that means that at least one dimension of space was compressed to nothing and lost when the space was transformed. And I touched upon that in the last video. And again, I'll recommend a video series by 3Blue1Brown on YouTube for its powerful visualizations of matrix transformation. Link to those videos in the description. So I'll close this presentation with the visual representation for why the determinant is 0 when the column space of a matrix is linearly dependent. And this is the same visualization I showed in the last video. As we know, the result of transforming a vector with a matrix will always be in the column space of the matrix. So if our columns are dependent, then the column space of a matrix is a space with lower dimensionality than the source vector. As such, at least one dimension is completely compressed to 0 in the transformation. So it follows from the math that the area, and therefore the determinant, must be 0 if any dimension is lost. Once again, I discussed this in a little more detail in the previous video in the series. In the next video, we're nearly wrapping up Chapter 2 of the Deep Learning book by walking through an example of a simple machine learning algorithm using linear algebra. So I hope this video has been helpful. Thanks for watching. Take care.